let's unpack this. You hear Android, and your mind probably goes straight to your phone, maybe a tablet, maybe your TV even, right? Or your smart TV. But what about your car? And I don't just mean plugging in your phone for Android Auto.
No, that's different.
We're talking about a full-blown Android operating system built into the car's dashboard, running natively. That's Android Automotive OS, or AAOS.
And that's really the core shift we're exploring today. Cars, well, they've become incredibly complex software platforms. I mean, really complex.
That's not what we're talking.
We're talking potentially over 150 million lines of code in some premium cars, spread across all sorts of systems.
Wow.
Yeah, and this whole digital transformation, it enables amazing new connected features, obviously, but it also brings up some fascinating engineering challenges and, really critical questions about security and privacy.
Especially when the computer is literally controlling parts of the machine you're driving.
Exactly. That's the crux of it.
So for this deep dive, we've got a great stack of source material you've shared with us. Research papers, articles, some technical overviews. We're going to peel back the layers, really understand what makes AOS tick. Our mission, really, is to guide you through its inner workings. See how it manages everything from, say, your music to system sounds. And maybe most importantly, understand the security and privacy measures they're building in.
Yeah, it's this interesting intersection, isn't it, where fast-moving consumer tech meets the, let's say, rigorous demands of automotive safety and reliability.
Definitely. So let's start with that fundamental question, the one that honestly trips a lot of people up. What is Android Automotive OS? And how is it really, truly different from Android Auto?
Okay. So at its heart, AOS is an open-source operating system. It's based on Android, but specifically engineered for the vehicle environment. You might sometimes hear it marketed as cars with Google built in.
Right, that's one version of it.
That's one flavor, yes, but it's not just an app layer, right?
Yeah.
That's the key.
No, not at all. And that's the critical distinction from Android Auto. People get this mixed up all the time.
They do. Android Auto is basically an application. It runs on your smartphone, and it just projects its interface onto the car's screen. It relies completely on your phone for, the processing, the connectivity, everything.
Okay.
Android Automotive OS, AAOS, that's the native operating system. It runs directly on the car's own computer hardware.
Okay. So think of it like with Android Auto, your phone is the brain. The car screen's just a monitor.
Exactly. But with AOS, the car is the brain. It's running its own dedicated OS.
Got it. The car itself is the Android device. Makes sense. When did this whole thing start?
Google introduced the concept back in March 2017. Some early adopters were manufacturers like Volvo and Audi. They jumped on board pretty quickly.
And adoption's picked up since then.
Oh, yeah, significantly. By 2023, sources suggest, 16 major auto brands had committed to using AOS in some form. You see it in cars from Polestar, GM, Ford, Honda, BMW, Porsche, Hyundai. The list goes on.
And there's an important point here, isn't there? Not all AOS cars have the same, Google ads.
Right. That's the AOSP versus GAS distinction. It's important.
AOSP.
GAS. Yeah, AOSP is the Android open source project base. It's the open source AAOS platform. Car makers can take this foundation and build their own infotainment system on it, use their own apps, their own services.
Right.
Then there's GAS, Google Automotive Services. That's Google's proprietary suite. Think Google Maps, Google Assistant, the Play Store.
Familiar stuff.
Exactly. Manufacturers can license that suite and integrate it into their AAOS system.
So some cars give you that familiar Google experience we know from our phones.
Precisely. Many models from GM, Ford, Renault, Volvo, they use AOS with GAS.
And others use the underlying AOS technology but build a completely custom interface on top, like their own thing.
Exactly right. Examples would be Stellantis' Uconnect 5, the Lucid Air, BMW OS 9, VW Group's One.infotainment. They use the AOS core for, stability and the car-specific features, but they provide their own unique user experience and maybe their own app store.
Shows the flexibility of that open source base.
It really does.
Okay, so we know what AOS is. It runs directly on the car's hardware. How is this whole system structured inside the car? What's the architecture look like in the sources?
Well, imagine it like a layered cake. It's similar, actually, to how standard Android works, but with layers specifically for the car.
Okay.
At the very top, you've got the applications you actually interact with, Spotify, your navigation app, whatever.
Right.
These sit on top of the standard Android framework and also some vehicle-specific services. Beneath that, there's a really critical layer. It's called the hardware abstraction layer, or HAL.
HAL. Yeah.
And then right at the bottom, you've got the Linux kernel talking directly to the vehicle's actual the chips, the sensors, the buttons, all that stuff.
And that HAL layer, specifically the vehicle hardware abstraction layer. The VHAL, that sounds like the crucial bridge, doesn't it?
Oh, it's absolutely fundamental. Think of the VHAL as like the universal translator for the Android software.
Translator.
Yeah, because every car's hardware is different, right? Different climate controls, different sensors, different button layouts.
Hmm.
The VHAL provides a standardized way for the Android system and the apps to talk to all that varied hardware. Doesn't matter the specific make or model.
How does it do that?
It translates software requests into hardware commands and hardware data back into software info, and it does this using something called properties.
Properties.
Yeah.
Like data points
Right.
or settings.
Exactly like data points. Each property represents a specific piece of information or maybe a function in the vehicle. Things like the car's current speed, pedal position, the temperature setting for a zone, whether the headlights are on, stuff like that.
Okay. Speaking of things like temperature zones and sounds, the car's a noisy place, right? Lots of audio sources competing. How does AOS handle all the different sounds? Music, navigation, calls, alerts?
Yeah, the audio system in AOS is, well, it's surprisingly complex. It has to be. It's designed to handle multiple audio streams at the same time and route them intelligently.
So all those sources you mentioned, music players, nav apps, voice assistants, the car's own beeps and boops.
Exactly. They all feed into this framework.
And it categorizes these sounds, doesn't it? To know what's what.
It does. It uses what they call audio contexts. This tells the system what kind of sound it is. The sources list things like music, navigation, voice command, call ring, alarm, notification, system sound.
Makes sense. So it knows an alarm should probably interrupt everything else.
Right. Knowing the context helps the system decide how to handle it. An alarm needs priority.
And this is where multi-zone audio comes in. That sounds interesting, especially for passengers. Introduced in Android 10.
Yeah, that's a key capability. Multi-zone audio allows the system to route audio to different physical zones within the car.
Like front and back.
For example, you could have the main cabin as a primary zone, and maybe a rear seat entertainment system or even different headphone zones as secondary zones.
So an app could play just in the back.
An app can request to play audio in a specific zone, yeah. And importantly, each zone can have its own separate volume control.
But the sources say it's not automatically tied to what's showing on a specific screen yet.
Not automatically assigned based on the display, no. That's what the sources indicate. And something for users to note. Typically, the physical volume knob or the steering wheel buttons, they usually only control the volume for the primary zone.
Ah, good to know. Okay, so you've got multiple sounds wanting to play. Music, navigation. A phone call comes in. How does the system decide who wins, who gets heard?
Right. That's handled by something called audio signal arbitration. Before Android 10, this was managed with something called audio focus. But in AAOS 10 and later, they brought in Care Audio Focus. It's more strictly enforced, and it uses an internal interaction matrix.
The interaction matrix sounds like a rule book. Like sound A versus sound B, who gets priority?
That's exactly what it is. The matrix, which we saw detailed in the sources, it defines how a sound that's currently playing, that's a row in the matrix, should interact with an incoming audio request that's a column.
Okay, give me a concrete example from that matrix, like music playing, then navigation.
Sure. So if you have music playing and a navigation prompt needs to come through, the matrix typically dictates that navigation is exclusive to music.
Exclusive meaning.
Meaning the system will either pause the music entirely or maybe duck. It significantly lower its volume so you can clearly hear the directions.
Okay. What about, say, a phone call ring coming in while navigation is talking?
The matrix usually defines those as concurrent.
Concurrent, so they play together?
Yeah, they can play at the same time. Because, you need to know the phone's ringing, even if you're getting directions right then. And this matrix, it's fixed by the car manufacturer based on the specific audio setup of that car.
And all this relies on the underlying hardware interfaces, the audio HAL you mentioned.
Yes, exactly. Configuring this whole system, getting it to work correctly with the car's specific amplifiers, speakers, signal processors, that's a significant engineering task.
Oh.
It's all handled via the audio HAL and these HIDL interfaces. Very hardware dependent.
Okay, let's jump back to that VHAL. The vehicle hardware abstraction layer, the translator. You mentioned it uses properties. Let's dig a bit deeper into how that works. Why is it so important?
Right. So the VHAL's core job is to provide that standardized way for any Android app or service to get vehicle data or control vehicle functions, no matter the underlying car hardware. And it does this by defining these properties as the sort of common language.
What kind of data can these properties actually hold?
Oh, a wide variety. The sources describe the different value types. Simple stuff like a Boolean true-false, like for a light being on, int32, or float for numbers like speed or temperature, string for text, maybe the VIN number,
Okay.
but also more complex types, arrays of values, raw bytes, epoch time for timestamps. There's even a mixed type for properties that might hold different kinds of data at different
And
times.
these properties aren't all the same in how they behave, are they? They have attributes.
Correct. Key attributes include read-write access. Can you just read the data, or can you actually change it, like setting the temperature?
Right.
And crucially, something called change mode. This defines how often you get updates. On change means you only get notified when the value actually changes. Useful for, say, switching day-night mode.
Makes sense. Only when it flips.
Yeah. Then there's continuous. That means you get updates constantly at a defined rate, essential for tracking things like vehicle speed or accelerator position where you need frequent updates.
And then there was area configs. That sounds like how properties link to different parts of the car.
Exactly that. Area configs links a property to specific physical zones or components, like seat rows, row 1 left for the driver, row 2 right for the rear passenger side, or specific doors, mirrors, things like that.
So that's how the system knows which temperature property controls the driver's climate zone.
Precisely. It uses the area ID.
So if an app wants to, say, check the speed or change the temperature in the back seat, how does it actually talk to the VHAL?
Apps use specific VHAL calls. There's a get call to read the current value of a property. If it's a property linked to an area, you need to specify the area ID, like row 2, right? For global properties like speed, you use area ID 0.
Okay.
Then there's a set call to change the value of a property for a specific area ID. And a subscribe call is really useful. You basically tell the VHAL, hey, let me know whenever this property's value changes, and you'll get updates for any area ID that property applies to.
That HVAC temperature example from the sources really highlights the complexity, doesn't it?
Yeah.
The same set temperature property might control just the driver's seat in one car. But in another car, maybe it controls the driver's seat and the rear left seat just because of how that specific vehicle is configured using area configs.
Exactly. The sources really emphasize this. The exact mapping of VHAL properties, especially for complex systems like climate control, is entirely dependent on the specific vehicle hardware and how the manufacturer configured it.
Which is why that standardized VHAL layer is so critical for app developers.
Absolutely. It hides that complexity.
And can car makers add their own special functions, things not in the standard VHAL?
Yes, they can. They can define custom vendor properties for unique features their car might have. These are accessed through separate APIs. The sources do note, though, it's important they follow specific guidelines and permissions for these, to avoid breaking compatibility or creating security risks.
Okay, so we've unpacked what AOS is, how it talks to the car, how it handles audio. Now, let's shift gears.
Yeah.
Let's talk about what is arguably the most vital consideration when you put a computer in charge of car functions: security and privacy.
Yeah, this is absolutely non-negotiable. You have cars with critical safety systems connected to the internet. A cyber attack isn't just about data theft anymore. It could potentially impact physical safety.
Yeah, the stakes are incredibly high.
The security of these systems is paramount, period.
And the sources definitely paint a clear picture of the growing threat, citing things like the automotive cybersecurity market size, the jump in incidents.
Yeah, the market's projected to grow massively, right? $9.7 billion by 2030. And connected vehicle incidents, they jumped, 59% between 2022 and 2023? That's huge.
And a lot of those are remote attacks.
Alarmingly high percentage. 68.2% were remote, meaning the attacker wasn't even near the vehicle. And the actors range from individual black hat hackers all the way to state-sponsored groups.
And regulators are stepping in.
Absolutely. Regulations like UNES R155, they're becoming mandatory globally. They require manufacturers to implement really comprehensive cybersecurity management systems across the entire vehicle lifecycle. AAOS is designed really to provide a strong foundation to help meet these complex rules.
So how does AAOS actually build this security foundation? What's the approach?
It uses a defense in-depth strategy. Think layers upon layers of security. So if one layer is somehow bypassed, hopefully Others are there to catch the attack.
Makes sense. Multiple walls?
Exactly. The sources detail, I think it was 5 key layers, designed to mitigate something like over 94% of potential attack vectors.
Okay, let's start right at the beginning. Secure boot. How does that work?
Okay, think of Secure Boot as the security guard at the front gate. It verifies everyone or everything entering the system when it starts up.
So when the car turns on.
Exactly. Secure Boot ensures that only trusted, cryptographically signed code gets loaded. It uses a hardware-based trust anchor and strong encryption like RSA 2048 to verify every single component in the boot sequence.
And the benefit.
It prevents malicious or unauthorized software from taking control before the OS even fully loads. The sources say it mitigates about 85.7% of boot attacks. And the impact on startup time is minimal, like 1.2 seconds penalty.
Okay, strong start. Then there's sandboxing. We know this concept from phones, but it must be even more critical here.
Oh yeah, crucial. Sandboxing is all about isolating software components from each other, keeping them in their own boxes.
Right.
In AAOS, applications are strictly separated using Linux process isolation and something called C-Linux.
C-Linux.
Yeah, think of it like digital walls with very strict access rules around different parts of the system. The sources mention 43 automotive-specific C-Linux domains, which is quite a lot.
Do it work?
Well, testing showed this containment worked in 94.4% of tested attack scenarios. And importantly, that VHAL layer we talked about, it's also isolated. That helps protect critical driving functions from less trusted software with really low performance overhead, about 3.8%.
And the system defines different trust domains too.
Correct. The architecture separates software into different zones based on how critical they are. You've got core vehicle functions, vehicle services, more trusted apps like built-in navigation, and then less trusted apps, maybe third-party media players you download.
Boundaries between them.
Enforced through very fine-grained permission checks. Sources mention 37 types. The idea is that breaking out of a less trusted domain to affect something critical usually requires chaining together multiple vulnerabilities, not just finding one flaw.
Okay, that's the architecture. Moving beyond that, how does AAOS manage who can access what? And securing the communication itself?
Access control is much more granular than on your phone. There are 4 distinct privilege levels, and these govern access to 86 different vehicle functions across domains like powertrain, chassis, body, infotainment.
So my music app can't just decide to, I don't know, hit the brakes or unlock the doors.
Exactly. No way. Access checks happen dynamically, continuously validating permissions. And its fast adds only about 8.7 milliseconds latency for these protected operations.
And it's context aware?
Yes, meaning permissions can actually adapt based on the vehicle's state, like is it parked or driving, what's the speed, things like that. 7 factors mentioned.
What about protecting the data itself, both when it's stored and when it's moving around?
Cryptography. It's used heavily. Data stored on the system, data at rest, uses strong AES 256 GCM encryption.
Okay.
For communication within the vehicle, like on the internal networks, messages use 32-byte message authentication codes, or MX. That prevents tampering or someone injecting fake messages. Testing showed this prevented 98.2% of those kinds of attacks.
And talking to the outside world, like cloud services.
That uses industry-standard secure protocols like TLS 1.3. With certificate checks to make sure you're actually talking to a legitimate service. Sources say this detected 94.7% of invalid certificates in tests. And all this encryption adds very little performance overhead, maybe 2.8 to 3.4%.
How does the system make sure the components it's talking to are legitimate?
Right.
Like verifying identity.
Right, that's authentication and key management. The system verifies the identities of components and services it interacts with. It supports various multi-factor authentication methods. Critically, the master cryptographic keys. They're stored in a hardware-backed secure element.
Special chip.
Yeah, a physically hardened chip designed to resist tampering and theft. It protects the really important keys used for encrypting data and verifying software. Keys used for, say, communication sessions are also rotated frequently, like every 24 hours or after so many messages for extra security.
These defenses sound pretty robust, but what about new threats? Things nobody's seen before, 0 days.
Good question. That's where threat intelligence and response come into play. AIOS includes intrusion detection systems, or IDS.
How's it work?
It uses a hybrid approach, signature-based detection to spot known attack patterns like antivirus software, but also anomaly detection.
Anomaly detection.
Yeah, it uses lightweight machine learning to identify unusual behavior that might indicate a new unknown threat, something that just doesn't look right.
And how effective is that?
The system showed high detection rates in tests over 92% for known attacks and nearly 77% for previously unseen ones. And importantly, it does this with minimal impact on performance or the latency of critical vehicle signals like CAN messages.
Can the system adapt? Can it learn about new threats discovered out in the world?
Yes, that's crucial. Threat intelligence signatures can be updated over the air, pushed out to the vehicle fleet. Sources indicate that new signatures could be distributed and active within about 28 hours of a threat being identified in testing. Pretty quick turnaround.
Software updates themselves.
Yeah,
They can be a weak point if not handled securely right.
absolutely. A compromised update could be disastrous. So, over the air, OTA software updates in AAOS follow strict security standards like SAE J3101.
How are they protected?
Updates are cryptographically verified using robust, hardware-protected, dual-signature validation. Strong keys, like 3072-bit. This verification process adds only a few seconds, maybe 4.2 seconds, to the update. But it's critical to ensure the software is authentic and hasn't been tampered with. It meets core security goals: authentication, integrity, freshness.
And if an attack is detected despite all these layers, can the system react automatically?
Yes, it has automated incident response capabilities. Based on the severity of the detected threat, the system can trigger one of 6 different response modes.
Like what?
Well, the most aggressive mode might involve isolating non-essential systems to prevent the attack from spreading. In tests, this prevented attack propagation in over 94% of cases. The system is designed to contain high-severity incidents very, very rapidly, often within milliseconds. Sources cite an average of 187 meters response time for critical threats.
And it logs what happened.
Yeah, it also captures forensic data about 2.4 ME/day per incident mentioned for later analysis to understand the attack.
Okay, that's a really deep dive into the security layers. Impressive. Now let's switch to the other side of that coin. Privacy. Cars collect a massive amount of data, don't they? Location, driving habits, how you use the system. How does AOS handle your personal information?
Yeah, privacy is just as crucial as security for building user trust. AOS aims to adopt a privacy-preserving approach right from the design stage. A key principle is data minimization.
Data minimization, meaning just collect less stuff.
Essentially, yes. Only collect the data that's absolutely necessary for the requested function or service. The approach is guided by how 14 different data categories are handled. Studies cited in the sources show this can lead to pretty significant reductions in data collection compared to older systems.
Like how much reduction?
Potentially up to 67% less location data, 42% less behavioral data. Data also has a graduated life cycle. Highly sensitive data might only be retained for very short periods.
And it can adapt based on where you are, like different privacy laws.
Exactly. Collection parameters can be context-aware. They can adapt based on user preferences, the vehicle's state, and even regulatory requirements like GDPR in Europe or CCPA in California. Ensures compliance across different regions. This approach was shown to eliminate over half, 58.3% of unnecessary data fields while still letting necessary features work.
But some data is needed, right?
Yeah.
For features like traffic analysis or improving services. How is that handled without identifying me or my car?
Right. That's done through data anonymization and aggregation techniques. They use methods like differential privacy.
Differential privacy.
Yeah, it adds carefully calculated statistical noise to data. This obscures sensitive individual details, but still allows for accurate aggregate analysis across many users. Another technique is K-anonymity.
K-anonymity.
That ensures individual data points, like your precise location, are always blurred within a group of at least K other individuals. So, for example, your location data might always be indistinguishable from at least 19 other vehicles if K equals 20.
Ah, safety in numbers.
Sort of, yeah. And for fleet-wide analytics, they can use secure multi-party computation. This allows insights to be derived from data across many vehicles without ever exposing the raw data from any single car or allowing individual identification. Adds a bit of overhead, but protects privacy.
Okay, all these technical protections are great. But how do I actually know what data is being collected? And how do I control my privacy settings?
Transparency and user control are fundamental pillars here. The privacy interface itself is designed for usability. It achieved high scores in studies. Privacy notices are layered, meaning you can get a quick summary up front, or you can tap to drill down into much more detail if you want it. Settings are organized functionally, making it easier for users to find and manage specific permissions, like data sharing categories. User testing showed high success rates finding settings.
And my choices stick. They don't reset after an update.
They're designed to be sticky, yes. Your privacy preferences should persist across software updates and vehicle restarts.
Wow. Okay. So pulling all of this together, what's the broader impact of having this level of security and privacy built into AAOS? What does it mean for the future of cars?
Well, first off, a robust security architecture like this directly enhances vehicle safety.
Hmm.
It helps prevent cyber attacks that could potentially interfere with critical functions. Sources suggest up to 70% of functions could be vulnerable in some scenarios.
So it's a safety feature too.
Definitely. And the investment in security offers a significant return compared to the potential cost, reputation damage, and safety risk of security incidents.
And privacy isn't just a nice to have, is it? It's foundational for connected cars.
Absolutely critical. Privacy concerns are consistently cited as a major barrier, 76% of experts in one source, to the wider adoption of connected vehicle technologies. Building trust through strong, transparent privacy practices is essential for the whole connected car ecosystem to thrive and for people to actually want to use new data-driven services.
Which leads us directly to the future. Maybe autonomous vehicles. Trust seems like it would be everything there.
It is the single most important factor, according to the sources we looked at. Transparent security measures, like the visible layers of defense in AOS, have been shown to increase people's stated willingness to adopt autonomous features by a pretty significant margin, 37%.
Interesting.
And things like rapid incident response, built-in auditing capabilities, they're key to building. And just as importantly, maintaining that long-term confidence.
And the research isn't stopping here. They're looking ahead.
Oh, far from it. The sources mentioned some really exciting future research directions, things like using more advanced AI for even smarter threat detection, exploring quantum-resistant cryptography to prepare for future computing power.
Quantum crypto. Wow.
Yeah. Applying techniques like federated learning for privacy-preserving data analysis across vehicle fleets, and even integrating safety and security concerns into a single, unified architecture right from the very beginning of the design process.
So wrapping up this deep dive, it's clear that Android Automotive OS is vastly more sophisticated than just mirroring your phone screen onto the dashboard.
Oh, absolutely. Night and day difference.
It's a complex, deeply integrated operating system, running natively in the car, managing core vehicle functions, handling tricky things like multi-zone audio, and underpinned by really extensive, multi-layered security and privacy measures built in from the ground up.
Yeah, it's a system designed not just for infotainment, but really to be a secure and trustworthy platform for the increasingly connected and intelligent vehicle we have today, and certainly the one we'll have tomorrow.
Which leaves us with this final thought for you, the listener. As our vehicles become more and more like computers on wheels constantly connected, collecting vast amounts of data, how do we collectively ensure that these incredibly complex systems, responsible for both our entertainment and our safety, remain fundamentally secure and protective of our most personal information? Not just now, but far into the future. It's a dynamic balance, isn't it? One we'll definitely need to keep watching.